In this video, we're going to be talking about residential duct design procedure, duct sizing, hair duct chart, hair duct sizer, external static pressure, devices pressure drop, available static pressure, friction rate calculation, equivalent and effective link, total effective link, pressure drop through supply and return duct, pressure drop through fittings and flexible duct, and the location of air handler unit and blower. Ductwork is an important part of every living space, which is designed to deliver the correct amount of airflow from a heating and cooling system to a living space at correct size and velocity. Duct has to be sized properly and must be balanced with the room heating and cooling loads. 50% of all the problems with the HVAC system, especially air conditioning in residential and commercial properties, is the ductwork. So the duct size and damper settings that determine the amount of conditioning air delivered to each room is important. The next thing we have to be worried is noise. Noise can cause a problem if air travels through the ductwork too quickly. We have recommended and maximums air velocities, so anytime we are dealing with air velocity, that means we're talking about feet per minute. We have two recommendations for the main supply and return duct, which are different for each ship. The recommended air velocities for residential should not be more than 900 feet per minute for the round main duct, 700 feet per minute for the main rectangular duct, 800 feet per minute for the return duct, 700 feet per minute for the return branches, 500 feet per minute for the rectangular supply branches, and 600 feet per minute for round duct branches. So that varies depending on what the use of building is. So velocity, if it's too high, it creates a lot of noise, and if it's too low, we're not moving enough air, and we could have condensation and dust building up in the ductwork. So the velocity needs to be proper according to the recommended and maximums velocities that matches both the International Residential Code and International Mechanical Code. When designing a duct system, the air handler should be installed in a central location of the building that allows you to minimize the length of the longest supply and return duct and keep duct runs as short as possible, and position duct to avoid obstacles and minimize the number of fittings required. And do not install a duct at the end of a plenum. That will cause to get too much airflow. Please install duct in the side of a plenum. A duct at the end of plenum will receive too much airflow that will be noisy. So in order to do duct sizing properly, you have to perform a room by room heating and cooling load calculation. You need to obtain the blower specification sheet, and you need to determine the external static pressure for using the blower data sheet. You need to calculate the device's pressure losses, such as coil, filters, supply diffusers, return grills, and dampers. and you need to calculate the available static pressure, and then you need to prepare a sketch of the Duct system, including registers and drill location, distance, and Duct fittings. You need to calculate the effective length for the Duct run, and then you will need to calculate the equivalent length or effective length for all the fittings. Then you need to calculate the design friction rate for the Duct system and design air quantity for each room and each section of the ductwork. The heating and cooling loads for each room are added to determine the total load. So loads of a building are expressed in BTUs per hour. So by knowing the correct heating and cooling loads, we can select the correct size of heating and cooling equipment. So all we do is a room by room heating and cooling load calculation to come up with a total load of a building. Then you can use an airflow friction chart or Duct sizer to determine Duct size for each section of ductwork. If required, convert round duct to equivalent rectangular duct size. So I'll make another video that how to convert the round duct to rectangular duct. The airflow through the blower depends on the speed of the blower and the pressure difference between the blower inlet and outlet. It's very important you have to look at the blower spec sheet. The blower spec sheet will provide a listing of airflow of the blower under various conditions. So let's say we are designing a system that requires an airflow of 1200 CFM at the external static pressure of 0.5. So in this case, I'm gonna use a blower speed of medium 0.5, which is sort of standard for the maximum static pressure. The pressure difference, the external static pressure between blower inlet and outlet is external static pressure. External static pressure is determined by the Duct system and will determine the volume of air delivered to the blower. The Duct system must be designed properly to achieve the external static pressure in order to deliver the proper air volume from the blower. If the static pressure is too high, the blower will not deliver enough air to match the loads. So if it's too low, the blower will deliver more airflow than needed. So the external static pressure is the amount of resistance through evaporator, supply duct, supply register, return grill, return duct, and filter before it returns to the blower. So the next step is to determine the available static pressure. The available static pressure is a measure of friction or resistance which the ductwork is designed to provide to the flow of air. This is used to design the longest duct run, so everything we do is based on the longest duct run from the air handler. So if we go to room by room, we may have a short or longer distance. We have to actually look at the length of ductwork, including the number of all fittings. Devices pressure losses are the pressure losses in the Duct system which can caused by devices other than ductwork. For example, an evaporator coil, depending on the coil, can have a different pressure drop. So if I select an evaporator coil with a pressure drop of 0.3, and if I had an air cleaner with a pressure drop of 0.2 inch of water column, it might not work the way we want to, so we'll need some ductwork adjustment or devices. We can start adding different features but with the lower associated pressure drop. For example, evaporator coil with 0.15 inch of water column filter, 0.08 dampers, 0.03 supply diffusers, 0.03 and return grills, 0.03 inch of water column. The available static pressure is a measure of the amount of resistance to the flow of air. So resistance results from the air contacting the interior surface of the duct. So this resistance in the system depends on the length of the duct, also the type of the duct. So the available static pressure is determined by subtracting devices pressure losses from the external static pressure. For example, if I have a system with an external static pressure of 0.5 inch of water column, an evaporator coil of 0.1 inch of water column, dampers with 0.03 inch of water column, filter with 0.08 inch of water column, supply registers with 0.03 and return grills with 0.1 plus 0.03 plus 0.08 plus 0.03 plus 0.03, that gives us 0.27. So I have now my 0.5 minus 0.27 equals 0.23. So I have now my available static pressure 0.23 inch of water column in order to size my duct properly. Therefore, my ductwork has to be designed with the 0.23 inch of water column because I'm no longer using 0.5. Additional resistance airflow occurs anytime when the air flows through a passage that is not straight or has a cross-sectional area. For example, the air has to flow through a 90-degree elbow or even a 45-degree elbows, offsets or reducers, so there is additional resistance in that fitting, so every fitting will have a pressure loss. When air passes through a reducer or an elbow, it will experience increase in resistance. Ducts are designed using the concept of effective length. The effective length of a duct is determined by adding the length of the ductwork to the effective length values for each fitting in that duct run. Here are some effective length or equivalent length examples from a track line, reducers, elbows, that we're going to use them for our next examples. Round branch, from a track line we have an effective length of 30 feet for that, return and supply elbows and reducers 5 feet depending on how tight that elbow is. In order to determine the effective length of each supply and return duct run, we must sketch it out. The sketch should include the location of all the supply and grills and fittings. Here is an example. The effective length or the total equivalent length of all the fittings. So we have 7 trunks, 4 reducers and 4 elbows, each of that associated with a different equivalent length of straight duct that give us in this example is 270 feet. We also have pressure drop equivalent length of straight duct through our supply and return PLNMs. 10 feet plus 15 feet gives us 25 feet. So we now have to look at the longest length of deck run for our supply and return deck. So we have 10 feet plus 10 feet plus 10 feet equals 30 feet for our supply deck, and 10 feet plus 10 feet plus 6 feet 26 feet for our return deck. So we now take the supply deck length which is 30 feet plus return deck length 26 plus the effective length of fittings 270 feet plus the effective length of supply and return PLNMs 30 feet plus the effective length of flexible deck which is 30 feet. So all these numbers give us the total effective length of 381. The total effective length is the longest length for supply and return deck run plus the equivalent length of flexible deck and all the fittings which can cause resistance to the flow of air. So we have added the supply and return deck run plus flexible deck and all the fittings to get the total effective length, which in this example is 381 feet. And then we determine the friction rate. So friction loss in a deck is the pressure drop resulting from the air contacting the inside surface of a deck. In deck design, friction loss is usually expressed in inch of water column per 100 feet of deck. The friction rate for a deck system is the friction loss or pressure drop along the total effective length that result in a pressure drop equal to an available static pressure. To find the friction rate, this formula will give you the friction rate to size the decks for system. FR equals ASP divided by TEL times 100, where FR is friction rate, ASP is the available static pressure, and TEL is the total equivalent or total effective length. So we now have 0.23 of available static pressure divided over 381 times 100. We come up with a friction rate of 0.0603 inch of water column. So in this case our friction rate is 0.0603 inch of water column per 100 feet of deck, and this is the number we'll use it to size the decks. So the big problem that lots of people have with the friction rate is they don't actually calculate it. They only assume it. The number they usually assume it is 0.1 inch of water column per, and so that's close to what we just calculated. But if you use 0.1 instead of 0.0603, our decks will be smaller or undersized. Do you know why they will be undersized? So if you test static pressure for some systems, undersized deck systems are very common, and this is because of 0.1 inch of water column, or a rule of thumb was used when designing the decks. So when we calculate the friction rate for a particular design, we're finding out how much pressure drop we can get away for each 100 feet of effective length of our deck system. If the friction rate is higher, it will allow us to size smaller deck and more restrictive decks. And if the friction rate is lower, it will allow us to size larger deck, and you have to use larger deck size for your system. Think of friction rate as pressure drop, it will make more sense. So note that always keep the available static pressure to be as high as possible and the total effective length to be as low as possible. So higher ASP is good and lower TEL is good, and both make the friction rate go higher. In the previous example, we had the total effective length of 381 feet with 0.23 of available static pressure, and we came up with a friction rate of 0.0603 inch of water column. Let's just increase the total effective length by adding more fittings and length of deck from 381 feet to 500 feet. To see what's gonna happen to our friction rate, as you can see in the second example, we have lots of fittings, and let's just say the total effective length for this design is 500 feet. Just divide the ASP of 0.23 by TEL of 500 feet times 100, we come up with a friction rate of 0.046 inch of water column. So in this example, friction rate of 0.046 is a lower number, which is not recommended because this will give us larger deck size and cost us more money due to change and speed up the fan. So the friction rate has to be more than 0.06 and less than 0.18, or somewhere between those numbers. So if the friction rate is too high, the fan will be too powerful and you need to decrease the blower speed or increase the total effective length. And if the friction rate is too low, that will result in inadequate fan performance, so you need to increase the blower speed or decrease your total effective length. So now let's start sizing deck by using our first example, which has the total effective length of 381 feet, and we came up with a design friction rate of 0.0603 inch of water column. Our design airflow is 1200 CFM coming through our supply deck, minus 60 CFM for a bathroom, and minus 200 CFM for bedroom 1, and minus 250 CFM for the kitchen, and minus 200 CFM for the bedroom 2, and minus 290 CFM for the dining room, and lastly 200 CFM for the bedroom number 3. So we now only need to size deck for the 1200 CFM, for the 940 CFM, and for the 490 CFM for our supply deck. And then we need to size for the 60 CFM, 200 CFM, 250, and 290 CFM for all the branches with flexible deck. So if we use an hair deck sizer or hair deck chart, we'll be able to determine the correct sizes and air velocities for each section of our deck. So in this example, we're going to use the hair deck sizer by plotting the amount of CFM for each section of our deck at friction rate of 0.06 inch of water column. As you can see on the deck sizer at friction rate of 0.06 for the 1200 CFM, we have a round deck diameter of 16 inches with an air velocity of 825 feet per minute and an equivalent rectangular deck of 11 by 20 inches. The next one at friction rate of 0.06 for the 940 CFM, we have a round deck diameter of 14 inches and 1/4 and half with an air velocity of 780 feet per minute and an equivalent rectangular deck of 11 by 16 inches. And the last one for supply deck at friction rate of 0.06 for the we have a round deck diameter of 11.5 inches with an air velocity of 690 feet per minute with an equivalent rectangular deck of 11 by 10 inches. For example, as you can see on the deck sizer for the 250 CFM, we have a round sheet metal deck with a diameter of 9 inches. Let's say the flex deck, we're gonna use it as a compression of 4%. So for a 4% compression, you can select a flex deck diameter of 3/4 larger than the round sheet metal deck. So in this case, instead of 9 inches round sheet metal deck, we can select 9 inches and 3/4 flexible deck. So all the sizes which has been indicated on the deck sizer, you need to add 3/4 inches larger than round sheet metal deck in order to get the right size for the flexible deck, which is a compression of 4%. So all the sizes which has been indicated on the deck sizer, you need to add a 3/4 inches larger than the round sheet metal deck in order to get the right size for the flexible deck, which is a compression of 4%. So you can add about 1 inches larger than the round sheet metal deck in order to get the flexible deck size, which is a compression of 4 to 10%. You can add 1 inch and 2/4 larger than the round sheet metal deck in order to get the flexible deck size, which is a compression of 15%. You can add about 2 inches larger than the round sheet metal deck in order to get the flexible deck size, which is a compression of 30%. So for round decks, you can also use hair deck chart. If you use an hair deck chart, it will give you the same result as the deck sizer for the round deck. As you can see, for the 1200 CFM, we have the same diameter of 16 inches with an air velocity of 825 feet per minute. And lastly, you can size your return by using the same way as we just did for our supply decks. So that's it for this video. Thank you for watching.